Hi students, in this video we are going to start the unit 2. So in that we are going to discuss about the Fourier analysis of continuous time signal. Before discussing about this topic, first we need to know why we have to go for this Fourier domain representation. Okay, so for example, consider I am having a signal like this. Okay, considered here signal like this. Okay, so here for this signal, so this is what a time period t. Okay, it is having an amplitude a. So I need to find out the frequency component present in the signal. What I will do, I can easily find the one cycle time period 1 by t. If I can easily find out the frequency component present in the signal. Suppose I am having I have done two signal that is added together. Okay, so it's somewhat like this. Okay, so I don't know how to find out the frequency component present in this signal. Okay, so it is difficult to find out the frequency component in time domain. Okay, so what we are going to do is, if we transform this complex signal in the frequency domain, we can easily find out the frequency component present in the signal, as well as we can reveal these some frequency domain parameters such as bandwidth, spectral content of the signal. We can easily find out the frequency related components in the frequency domain. So in order to realize these complex signals, we need to convert this complex signal in time domain into an frequency domain. So in order to convert the signal into frequency domain, what we need to do is we are going to perform transformation. We are going to perform a transformations. That is not transformation, we are going to transform in time domain to the frequency domain. Okay, so here we know that in order to perform this, here we are having some classification. So you know that the signal can be classified as continuous time signals and discrete time signals. So in continuous time signals there are two types, periodic and aperiodic. Discrete time, we are having periodic and aperiodic signal. Okay, so you know what is periodic signal? That is, this signal is repeating every time, that is periodic. That is x of t plus t equal to x of t. So this is your periodic signal. Now here, if we want to realize the frequency analysis, we want to reveal the frequency domain parameters of such signals, what we need to do is we are going to perform continuous time Fourier series. If you want to perform for aperiodic signal, if you want to analyze these frequency domain parameters for an aperiodic signal, we are going to perform continuous time Fourier transform. Similarly, for discrete time, if it is a periodic, we are going to perform discrete time Fourier series. For aperiodic, we are going to perform discrete time Fourier transform. In the first unit, what we are going to see is we are going to discuss about this CTFS. Later we will discuss about the CTFT. So okay, first we will discuss about Fourier series, that is continuous time Fourier series, in detail in the second unit. So here now we will discuss about continuous time Fourier series. This continuous time Fourier series is meant for periodic signal, that is x of t plus t is equal to x of t, and from this, if it is a continuous signal with a period t, you can find out its fundamental frequency ohm naught is equal to 2 pi by t. And also here, what is the significance of this Fourier series is that any continuous time signal can be represented as a linear combination of harmonically related complex exponential. So here a signal is x of t. Consider this is a signal x of t. This can be represented as a linear combination of harmonically related complex series. For example, you know that sine omega t, right? This can be represented as e power j omega t minus e power minus j omega t divided by 2j, right? So this is what your exponential. We are representing the sine signal in terms of exponential. And also cos omega t you can represent as e power j omega t plus e power minus j omega t divided by 2. So we can represent this in terms of complex exponential. This is what known to us, so we have represented this like this. So there are unknown signals are there, so many unknown, that is unknown representations are there. So we are going to represent any continuous time signal by using a linear combination of harmonically related exponential series. Okay, so now here x of t is equal to k summation k equal to minus infinity infinity a k e power j k ohm naught t. Here when k equal to 0, what you will get is, you will get e power 0, you will get a constant a naught alone. So this is called a DC component of the signal. Okay, when k equal to plus or minus 1, which this represent, that is when you have plus 1 you will have a1 e power j ohm naught t. When you have minus 1 you will have a minus 1 e power minus j ohm naught t. Okay, so this represent the fundamental component, first component. This represent the first harmonic component or fundamental component. This is said to be a first harmonic component or the fundamental component. Okay, and similarly k equal to plus or minus 2 represent the second harmonics, and k equal to plus or minus 3 represent the third harmonics. Okay, so ak is this is the weight corresponding to the kth sine wave component of the frequency k ohm naught, and it is referred to as a Fourier series coefficient. Okay, so this kth, that is ak, represent the kth sine wave component of the frequency component k ohm naught, and it is referred to as the Fourier series coefficient. Okay, now next we are going to find out the magnitude and the phase spectra. Okay, for any signal you can represent this magnitude at phase spectra. Okay, so here what we are going to do is consider n coefficient ak, this coefficient. Okay, this coefficient can be represented as magnitude and the phase spectra e power j ak. Okay, so for example, what is the meaning is, here this we are representing in polar form. If you are having a plus jb, so how will you find out the magnitude? You will find out magnitude a square plus b square and angle as tan inverse of b by a, right? So like that you will find out this magnitude and phase. Similarly here this is the rectangular form. Okay, here now we are going to consider the polar form, and here ak equal to magnitude of ak e power j angle of ak. So this represent the magnitudes, and this represent the angles of various exponential component. The magnitude of ak versus the angular frequency is called the magnitude spectrum. Okay, so that is, we are going to draw this magnitude coefficient versus frequency component, then it is called the magnitude spectrum. And if we are going to draw angle versus the ohm, that is the frequency, it is said to be a phase spectrum. Okay, so these two plots together are called frequency spectra of the signal. So what is the frequency spectra of the signal? Frequency spectra is nothing but magnitude spectra and the phase spectrum. These two represent the frequency spectrum of the signal. How will you find magnitude and phase spectra? First in polar form. Here this represent the magnitude part and this represent the angle part. That is, we are drawing that is magnitude versus angular frequency ohm. It is said to be a magnitude spectrum, that is ohm here. If they are drawing an angle versus this is magnitude versus angular frequency is the magnitude spectrum. Angle versus ohm is said to be a phase spectrum. Okay, so this is what the thing you need to know before we are going to enter into the continuous time Fourier series. And also here, see here, this when you here this summation k represent the discrete values, right? He it takes the value at discrete instance, so this is said to be a discrete frequency spectrum. Now consider the problem. We need to find the Fourier series representation of a signal, of the signal x of t is equal to sine 2 ohm naught t, and we are going to plot the frequency spectrum. Okay, so what is the first step? If you understand this problem, you will easily understand what is magnitude and phase spectrum. Okay, so whatever the signal given, so first represent this signal in terms of exponential series. Okay, this is represented as e power j 2 ohm naught t minus e power minus j 2 ohm naught t divided by 2j. Okay, now write this as 1 by 2j e power j 2 ohm naught t minus 1 by 2j e power minus j ohm naught t. Okay, so this is what your x of t. Now consider this equation. What is the equation? Represent x of t is equal to summation k equal to minus infinity to infinity a k e power j k ohm naught t. So this is what the that is any continuous time signal we are going to represent as a linear combination of harmonically related complex exponential. Now compare these two equations. So here so many summations are there, but here only two summations are there. Okay, so when you compare these exponential, now see the k value. What is k having? K taking the value of 2 here. Here it is taking the value of minus 2. Okay, so here we know that only two coefficients are there. One at k equal to 2 and another at k equal to minus 2. Okay, so this I am going to represent it as a2 as 1 by 2j. Okay, and a minus 2 as just we are going to compare these two. This is what the magnitude, right? When you compare this is what the magnitude. So this is equivalent to this one. Okay, so here a2 is equal to 1 by 2j, a minus 2 is equal to minus 1 by 2j. Now what we have obtained? We have obtained two coefficient, one at k equal to 2 and another at k equal to minus 2. How I obtained these two? Just by comparing these two. Here u power e, you are having e power j, you are having ohm naught t. For k, what is the value you are having? K equal to 2 you are having. So k equal to 2 and k equal to minus 2. So I am having a2 is equal to 1 by 2j, a minus 2 is equal to minus 1 by 2j. So here, now here I am going to find out the magnitude and phase spectrum. Okay, so this ak can be represented as magnitude of ak e power j ak. So now here this a2 I am going to represent it as 1 by 2j. This I am going to represent it as 1 by 2 e power minus j pi by 2. So why I am representing this? I need to represent in terms of magnitude and phase part. So I am going to represent this j as e power minus j. So you know that this can be represented as j can be represented as numerator minus j, right? 1 into minus j divided by 2. So minus j is nothing but here if you choose this, what you will get? You will get cos pi by 2 minus j sin pi by 2. So what is the equivalent value of this? Cos pi by 2 is 0, sin pi by 2 is 1. So you will get which is equivalent to minus j. So this minus j you can represent it e power minus j pi by 2. So I am representing this minus j as e power minus j pi by 2. Okay, now I have represented this as magnitude part. So your a2 is nothing but your 1 by 2, and when you compare this two, so what you will get? The magnitude of ak is equal to minus pi by 2. Okay, so this is what the coefficient we have find it out. Okay, so the next one is a minus 2. A minus 2 is nothing but this one. minus 1 by 2j. Similarly, I am going to represent this. This can be represented as 1 by minus 1 by 2j. So I am going to write it in the numerator. So minus j. So j by 2. So this can be written as 1 by 2 e power j pi by 2. So e power j pi by 2 is here cos pi by 2 plus j sin pi by 2, you will get j. So now here the magnitude of a minus 2 is 1 by 2. The angle a minus 2, sorry, here it is 2. a minus 2 is pi by 2. Okay, so it is pi by 2. Now what I need to do is I am going to draw the frequency and phase spectrum. Okay, so here this is the frequency spectrum. In the frequency spectrum there are two spectrum. One is magnitude spectrum and phase spectrum. So here one at discrete values I am drawing minus 1 minus 2 because only I am having 2, so it is enough to draw up to 2. So at k equal to 2, here see k equal to 2, what is the magnitude? The magnitude is 1 by 2. At k equal to minus 2, what is the magnitude? It is also equal to 1 by 2. So this is what your magnitude ak versus k, discrete component, that is discrete frequency component. Okay, so next one is phase spectrum. Here magnitude ak, here also 1 2 3 minus 1 minus 2. Here at a2, what is the magnitude? Here it is minus pi by 2. So here it is minus pi by 2. At plus 2 it is plus pi by 2. Okay, so this is what your magnitude and the phase spectrum. So here for a signal we have represent in terms of exponential series. From exponential series we can find out the frequency component, that is the magnitude as well as the phase component. Now see this problem, x of t is equal to cos ohm naught t. So similarly I have represented in exponential series e power j ohm naught t plus e power minus j ohm naught t divided by 2. So I am representing 1 by 2 e power j ohm naught t plus 1 by 2 e power minus j ohm naught t. I am going to compare with this equation. Now compare this coefficient. Here you are having j ohm naught t for k you are having 1. So I am having k equal to 1 and k for this k equal to minus 1. So here the coefficients are a1 and a minus 1. So the magnitudes I am going to consider the coefficient ak. So for that I have taken 1 by 2. Here it is my a minus 1, it is 1 by 2. So here consider, see here it is having only real value, there is no j term. So here if there is no j term we may we may not able to represent, write it in e power j theta. Okay, so here there is no phase part, only magnitude is there, therefore no phase spectrum, because it is only a real, if it is a real value only you will have magnitude, no phase spectrum. Now I am going to draw this with coefficient 1 it is 1 by 2, at coefficient minus 1 it is also 1 by 2. So this is what your Fourier series representation of cos ohm naught t. Now consider this example. Here you are having 5 cos pi by 2 t plus pi by 6. Similarly I am representing in exponential e power j theta plus e power minus j theta. So here 5 by 2 outside, taking 5 by 2 outside, this can be represented as e power j pi by 2 into t e power j pi 6 j pi by 6 plus 5 by 2 e power minus j pi by 2t into e power j pi by 6. Okay, now comparing with this equation, now see here the coefficient. So what here we may not able to compare with this because this is an additional term. Well, this belongs to this coefficient ak. Now we are going to compare only with this equation because it is having only t. So I am comparing this here. Here there are two terms are there, j and t, but for k ohm naught you are having pi by 2. This k cannot take the value of pi by 2 because it is the discrete value. Okay, so here ohm naught I am considering as a pi by 2. Then k equal to, if ohm naught is equal to pi by 2, k equal to 1 and k equal to minus 1. Okay, so here a1 equal to 5 by 2 e power, so this is the coefficient now a1, so a1 is equal to 5 by 2 e power j pi 6, a minus 1 is equal to 5 by 2 e power minus j pi 6. So this can be represented magnitude part and phase part. So this represent the phase term. So magnitude a1 is 5 by 2, angle is pi by 6. Here magnitude is 5 by 2, angle is minus pi by 6. Now consider this problem. Here you are having two signal. One is sine 60 plus cos 40. It is added with a DC that is a DC signal 1. Consider the first step. X of t is equal to 1 plus e power j 60 minus e power minus j 60 by 2j plus e power j 2t plus e power minus j 2t by 2. Okay, now I need to compare with this. Okay, now see these two terms. Here also, how you can find omega naught? K omega naught is equal to 6. Here k omega naught is equal to 6. Here k ohm naught is equal to 2. That is k ohm naught is equal to 6 for this term, k ohm naught is equal to 2 for this term. Okay, now here if there is a signal or added, there should be a common ohm naught. Okay, so here we are going to find here as GCD of 6 comma 4. I am going to take the common factor. Okay, so it is 2. Okay, now I am going to represent this 6 as e power j 3 ohm naught t minus e power minus j 3 ohm naught t. When I substitute ohm naught is equal to 2, I will get 6 here. When I substitute ohm naught is equal to 2, I will get minus 6 here. Similarly, here I substitute ohm naught is equal to 2, I will get, sorry, this is 4. This is 4, right? So this is 4. When I substitute ohm naught is equal to 2, I will get 4. When I substitute here ohm naught is equal to 2, I will get minus 4. Okay, now I got this term. So if you are having more than one signal added, you need to do one extra step. That is, we need to find the fundamental frequency ohm naught by taking this GCD of 6 comma 4, which is equal to 2. Okay, now here this I have find out. Here it is 2, so I am representing this form. From this, now compare this equation k equal to 0. Here this can be represented e power 0, so k equal to 0. Here when you compare this, k equal to plus or minus 3, here k equal to plus or minus 2. Now a equal to 0, a naught is equal to 1, so magnitude is 1, angle is 0 since it is a real term. So here consider 2, the magnitude is 1 by 2, so the term ak is a2 is 1 by 2, so it is real, so you will have only the magnitude. A2 is equal to 1 by 2 and A2 is equal to angle A2 is equal to 0. Now consider a minus 2. In this, a minus 2 is also 1 by 2, and case magnitude is equal to 1 by 2, phase is 0. Now consider a3 it is 1 by 2j, so this can be represented e power j pi by 2, so the magnitude is 1 by, that is the magnitude is 1 by 2 and the angle is minus pi by 2. Here a minus 3 is equal to minus 1 by 2j, which is we can represent as 1 by 2 e power j pi by 2, and here magnitude a minus 3 is 1 by 2 and the phase is pi by 2. So like that you need to represent if you have more than one signal. So if easily you can find out the frequency component present in that signal. That is, we are having frequency component at 3, 2 and a naught. If it is difficult to find it in time domain, so we can easily find out the frequency component present in the frequency domain. I hope you have understand this concept. In the next class we will discuss about the determining Fourier series coefficient, that is CTFS, in using analysis equation. Thank you.